Good evening. I would like to welcome you all here to the Baker Institute and welcome you for a very fine evening, I think, what is commonly referred to as Yuri's night. And I think we have an excellent speaker who can speak certainly to the space program and its future and where it's going and where it's been. And we're very pleased also to have the Consul General of the Russian consulate here in Houston is with us this evening as well. So thank you for coming. But this is a very important day because Yuri, we say Yuri's night, but this is the 50th anniversary of Yuri Gagarin's flight back in 1961. And for those of you that were here before we started the program, we showed a video that showed you some of the highlights from Yuri Gagarin's flight and showed you the launching pad he launched from. And last week we had cosmonauts and an astronaut from America launch from that very launch pad, going up to the International Space Station, and they successfully docked last Thursday evening and again came up from that same launch pad that Russia's been using so well for these many years. This is also the 30th anniversary of the Space Shuttle's first flight. That was in April 12th of 1981. So it's the days kind of matched up, but that wasn't done with really a lot of forethought. That just happened that way. So, but it turned out to be a good match. Our speaker this evening is an astronaut that has flown 5 times in space. He flew on the initial flight of the Space Shuttle Discovery and became very famous on that at least on the aborted flight, because we tried to get that vehicle off the pad and the engine shut down after they started. And he's very famous in the space program for making the comment that I thought we'd be a little higher than this at main engine cutoff. So, but we did manage to get Discovery off, and Steve flew Discovery for 3 flights and then flew Columbia for 2 flights, his first flight in '84, and then he also flew another flight in '86, and those were satellite deployment missions. And then he started to get into some very serious work when he took up the Hubble Space Telescope on his next flight, and then also went up on a servicing mission to the Hubble Space Telescope. And that turned out to be quite successful. And then he decided to go on a flight up, taking the Chandra X-ray Observatory up. So he also did that in '99. So he's had a great history with the space program, and I think is now back at his alma mater where he got his bachelorate degree at University of Kansas and is a professor there now. So let me turn it over to Steve Hawley.
Thank you, George, and thanks to all of you. Happy anniversary. It is a delight to be with you this evening on this special occasion, and I also want you to know how much I appreciate the honor it is to stand at this podium where so many famous people have had the opportunity to address this room, and it's humbling to think of myself in that company. I hope that I have something tonight I can share with you that you'll either find interesting or new or humorous or something, or some combination of those things. It's hard after 30 years to figure out how to boil down the engineering, scientific, and cultural achievements of the space shuttle into 30 or 60 minutes. So I'm definitely going to skip stuff that you probably think is really important. I'll skip over stuff that I think is really important. These are just, and you all probably have different impressions of what this heritage represents, but I hope you find something in here that you can enjoy. See if I can get this to work. Okay. Well, in the space program, I would just power cycle it. We'll see if we can. Let me just.
Sorry.
Sure.
Huh. Right.
Do it the old-fashioned way. No,
That's
that didn't
not
work
even
either.
Working either. Reboot.
Well, let me mention that a lot of what motivated me to want to talk about this topic tonight was the fact that I had the opportunity to be part of the editorial board for a new book that's coming out. Wayne Hale, the former Space Shuttle Program Director, former Ascent Flight Director, former Shuttle Flight Controller, was the managing editor. And the book is called Wings in Orbit, and Wayne felt appropriately that in the heat of battle, people forget or don't take the time to write down the important things that they do. And he didn't want to see the program terminate without trying at least to capture some of what was the legacy of the shuttle program. And so I wanted to try to take some of the things that we thought about as we put that book together and talk about them this evening. This is a very beautiful picture of the Shuttle Discovery rolling out for what we thought was going to be the last time. Turned out this was last November, and we had a problem on the pad with the tank, and so we actually rolled it back. This one wasn't my fault. But as you know, Discovery did fly for the last time in February, I believe, and on the right you see the landing at Kennedy Space Center, and on the upper left you see Discovery landing for the first time out at Edwards. And I was privileged to be somewhere right behind that window as we touched down. Hank Hartsfield was the commander, and it was a beautiful landing on the lake bed out at Edwards, but the running gag and the training for all of the months leading up to the flight was every time we would have a landing simulation and Henry would land the vehicle, Mike Coates and I would say, "Nice landing, Henry. I really think we could walk to the runway from here." This is the book that I mentioned, Wings in Orbit. It should be available right about now. And if you're interested, you can go to www.shopnasa.com and get a copy. There's a lot to talk about. Some of the important shuttle capabilities that I thought about as I was preparing some of these slides was the fact that the shuttle is very, very capable at transporting people and cargo to orbit, but perhaps as importantly, to bring cargo and people back. And I truly think that's a capability we'll miss when we no longer have the shuttle, that we can't bring significant amounts of experiment data, hardware back from orbit. There was a time when we had, I guess, questions early in the program about how precisely we could insert into orbit and how precisely we could point the shuttle, and turned out we could do that with precision. I'm amused as I wrote down relatively benign ascent environment. It reminds me of what people used to talk about when they refer to minor surgery. That's surgery they do on somebody else. You know, relatively benign ascent environment is Bill's. Mine was pretty exciting. It had a tremendous capability to let us do work in space, and in particular, initially with the Hubble servicing missions, and then now with routine operations to space station, where we do multiple EVAs, and we do EVAs with robotics, and put that remarkable facility together, and then come back and land on a runway. As you know, it has no engines once it enters the atmosphere, and so it's all about energy management as you glide halfway around the world. I touched down on a runway. Routinely flies at hypersonic speeds. We built the most efficient chemical rocket engine ever, and the largest solid rocket motors ever to fly. And the whole thing's reusable. It's remarkable. Launched nearly 400 people into space, carried more than 50% of the mass ever put into space by anybody, and as George indicated, launched and serviced the great observatories except for Spitzer. And we invented a whole new language. Some of you are NASA types, and so you'll understand it. But for the rest of you, I apologize if I slip into acronyms from time to time. Even having been away from the program for a few years, it still comes back to me. Think about the fact that the shuttle program has spanned 8 different presidential administrations, going back to Nixon. And I remember, coincidentally, I was actually at KU as a student when I think it was Tony England called John and Charlie on the lunar surface during Apollo 16 and told them that the space shuttle had been approved. And ever since then, development and the initial flights, Challenger accident during President Reagan's time, during George H.W. Bush and President Clinton, the program matured, and then under George W. Bush, the Columbia accident and the new vision, and now the program comes to an end, and we'll see what's next. It's worth thinking back maybe to the 60s. We were in a race to the moon. Apollo was perceived as costly, and once we had made it to the moon, the program lost its appeal, and that's why there are 3 Saturn V rockets sitting on their sides around the country. And this new concept called the Space Transportation System was developed. A reusable spacecraft that was to be flexible and cost-effective. And a new type of spacecraft that would demonstrate America's ingenuity. I'll show you in a second that we didn't quite live up to our promise of cost efficiency. Back to the original RFP, it's worth thinking about what the shuttle was originally envisioned to be able to do. We had these things called design reference missions, and one of them was a 65,000-pound due east launch to 100 miles. Another was a high inclination orbit out of the eastern range, and then there was this mission 3A, which was a western test range launch into a high inclination orbit. And that had implications for the design of the system that we lived with throughout the program. We actually never flew the shuttle out of the western test range, although we were planning to. And that was one of the consequences of the Challenger accident. But the requirement to be able to launch and go once around and land meant that you need to have a lot of cross range, and that led to the design of a delta wing vehicle. And the large payloads anticipated to be flown required a large payload bay. And 3Gs was the max acceleration for launch, and that was not for people, that's for payloads, so that designers know what to design to. And we're going to fly 500 and then 100 flights per airframe. And in the beginning, we were going to be able to fly the shuttle back with air-breathing engines. So that was kind of how it looked back in the 70s. And a reality check, even earlier than this, we promised more flights per year than that, but early in the shuttle program, we're talking 12 to 20 flights a year, and the reality was 6 to 8 was about what we were able to do. The vehicles were certified for 100 flights, and combined, hopefully we'll have flown 135 flights by the end of the summer, and Discovery was the vehicle with the most flights at 39. Clearly, the projected flight rates were overestimated, and that led to underestimate of what the real cost would be, and also it was a little more labor intensive to maintain than we had originally thought. And there were some key engineering challenges that we faced. This liquid engine, this high performance liquid oxygen, liquid hydrogen propulsion system, 500,000-pound thrust class, 50 missions without an overhaul, that's tough stuff. Today, it's still the case. It's a tremendous engine, but it does require some attention and care. The thermal protection system was challenging, and maybe some of you remember before the first shuttle flight, that was one of the long poles in the tent, trying to make sure that the tiles would stay on the vehicle. I told people over the years that I would love to have been in the room when some young engineer walked into his boss, presumably, and says, "Hey, boss, I got it figured out. All we need to do is paste 32,000 of these tile all over the shuttle, and then it can re-enter." You know, and some guy thought that was a good idea, so that's what we got. The other thing, they're really fragile, too. And when I was at Ames, I did a couple years at Ames back in the early 90s. Ames was integral in developing the technology that led to the tile. And the new astronauts that would be selected would do the tour of the NASA centers, and they'd come out to Ames, among other places. And the aerothermal guys would give them the tile. And they would say, see what this feels like. You know, put your thumbs on it. You know, we would spend the rest of their careers trying to teach them not to touch the tile. It had to take off like a rocket, land like an airplane, and operate in orbit like a spacecraft. That's a challenging thing to do. And early in the program, there were these ideas about having it be fully autonomous, and we never managed to achieve that. This is a chart that I got a long time ago from Mac Henderson, those of you that know Mac, of the flight rate as a function of time. And it's interesting to note where on this STS-1 took place. So it's kind of right there. So prior to that, we were advertising something like several dozen flights a year. And in fact, the largest actual flight rate, I think, is about 11, and that was from January 85 to January 86. Most of you know this, but this is the Space Transportation System. Technically, this is the orbiter. It's referred to commonly as the shuttle, but it's the orbiter. And the orbiter hangs on the side of the external tank with 2 big solid rocket motors and 3 liquid main engines that get it into orbit. This is a typical mission profile where it launches with the 2 solids firing after the 3 liquid engines have been ignited and checked out by the computers. That was what didn't happen properly on the one attempt George was describing. The solids burn for a couple of minutes, and then they're jettisoned, and you continue to ride on the liquid engines until you reach the proper MECO targets. And it's a very violent and noisy ride while the solids are attached and burning, but it becomes very quiet and very smooth, very purposeful once the solids come off. In fact, I remember in training for the first mission on Discovery, I was briefed, and I knew that when the solid rockets come off, the acceleration drops. You build up to something a little under 3 Gs when you're on the solids, and then the solids separate, and the acceleration drops. And then it continues to build again until you get to orbit. Well, you know, knowing that intellectually and having it actually happen to you are 2 different things. And I remember very vividly when the solids came off and the acceleration dropped, I immediately looked at the engine gauges because I was sure that everything had quit. But no, it all worked fine. Then after, you know, some number of days on orbit, it comes back, glides in, and lands on a runway. The fastest winged hypersonic aircraft in history. It's really remarkable that we can routinely fly at these speeds. And someday when that's routine, the legacy of the shuttle will have been key to the development of those technologies. John Young, commander of STS-1 30 years ago today, is a very quotable guy. And I always liked this quote. Hopefully you can read it, but if you can't, it says, anyone who sits on the top of the largest hydrogen-oxygen fueled system in the world, knowing they're going to light the bottom, and doesn't get a little worried, does not fully understand the situation. John said lots of things that stuck with me, and that was one of them. I remember another one. It wasn't, STS-1 didn't come very many years after the Apollo-Soyuz test program, and I remember John was asked at a press conference prior to STS-1 whether he thought additional Russian-American cooperation in space would be beneficial, and I remember John's answer was, yeah, he thought we ought to fly STS-1 with a Russian crew. Originally, I'm going to talk a little bit more about the redundancy and the design philosophy, because I think it's really interesting. But originally, we had the requirement for the program was that you could suffer a failure and still land somewhere. Ideally, if you suffered your failure late enough, you wouldn't have to land till the end of the mission, and you could do this thing called abort to orbit. If you have to abort, that's probably the best thing to do. Alternatively, depending on where you lose an engine going uphill, you may be able to go once around and land at Edwards Air Force Base. And if you have an engine failure early in the program, then the plan was you could turn around and fly back and land at Kennedy Space Center. That was called the return to launch site abort. That's another John Young quote that I remember. We never did one. Hopefully we'll never do one in the history of the shuttle program, but I remember John telling me once that, yeah, the only thing it really took to make an RTLS abort successful was 3 consecutive miracles and 2 independent acts of God. But when we got close to STS-1, the mass of the shuttle had grown to the point that we had this thing called an abort gap, which said there were places where you could suffer a failure and not be able to turn around and come back to Florida, but not have enough performance to get to Edwards. And the program had to come up with a plan. What are you going to do in that case? And the program came up with this thing called TAL, called Transatlantic Abort Landing. And it was, I remember back when John and Kripp were training for STS-1, because that was this kind of came up late in the game, and it was a really complex thing to do. And unlike normal entry where you have the computers to help you, the computers didn't really understand this thing called TAL. So there's a lot of manual stuff you had to do to make that work. Performance issues were a problem for us actually throughout the program. Ascent loads were something we had to pay a lot of attention to. We throttled the main engines. We actually even shaped the pour in the solid rocket motors to manage the aerodynamic pressure through ascent. And you design the mission to sort of the normal climatological conditions for the month in which you intend to fly, but sometimes you fly different than those conditions, and you have to do these assessments. As I said, this transatlantic abort landing option was kind of late in the game before STS-1, and all of that sort of was driven by performance issues, and it added complexity to shuttle development. And as I mentioned, the main engines were behind schedule. In fact, prior to STS-1, the main engines were kind of blowing up all the time, and that wasn't, real encouraging. This was really technically complex stuff, and as I mentioned, we had the problem with the tiles staying bonded on, and that resulted in delays and additional costs. I remember when I showed up in Houston in 1978, there were some people that had started this chart, which was a graph of time to launch for STS-1 versus time. And as you might guess, it was kind of going up. Which says every day you go, launch gets farther and farther away. I don't remember when that finally turned over. But it worked. The main engines have been remarkable. They are the most powerful chemical engines ever developed. The Saturn engines had more thrust, but the shuttle engines are more efficient. And I don't remember where I got that, whether I got it, maybe it's in the book, but if your car engine developed the same power per pound as the shuttle engine, it would be about the size and weight of a loaf of bread. So this is tremendous technology. And the heat-resistant tiles worked. We figured out how to keep them on, and they protected the vehicle. And some of that technology is finding its way into more common applications. And over time, as we learned how these tile performed, it was possible to replace the tile in some areas with blankets that were capable enough for the temperatures that those areas would see. And that was a lot better in terms of processing, and it was a lot better in terms of damage resistance. Main engine, just some gee whiz statistics. The specific impulse is about 450 seconds, which is pretty close to the theoretical limit you can get from liquid oxygen, liquid hydrogen. It's about 500,000 pound thrust at 100%. We actually flew routinely at 104%. And if I remember right, the pad was designed for 100%. So what we did was we launched at 100% and then immediately throttled up to 104% once we got away from the pad, so we didn't have to redesign the pad. We drain a swimming pool in about 25 seconds. It really pulls the fuel and oxidizer through the engine. And these are tremendous operating conditions. The high-pressure oxidizer turbo pump operates at 8,000 RPMs, the fuel turbo pump at 35,000. The temperatures and rotational velocities in the engine are amazing, which is why one of the safeguards we have in place is to make sure that the engine shuts down under pressure. What you really don't want to do is run out of gas with the engine operating, because the turbines will overspeed and it'll fly apart, and you probably take the back end off the vehicle. When we launched on our second mission, Hoot Gibson was the commander, and that was, I think we delayed 6 times or 7 times trying to get that one launched. And right after we lifted off, we got a message from the computer that said, "You're leaking helium." Now, helium is really important for a couple of reasons. It operates the valves in the main engines, but it also keeps the hydrogen and oxygen apart until you want them to come together. And the system is designed so that if you run out of helium, the engine will shut down, even if you want the engine to keep running, because if it does keep running, the engine could fly apart. So we were leaking helium, and I remember who called the normal call, you know, Houston, Columbia roll program, we're working a center engine helium leak. Might have been a right engine, I don't remember. And the control center said, "Roger." Now, I don't know, you know, if you're aviators, you may know what Roger means. Roger basically means, "I hear you." So we go on for a while, and Charlie Bolden was the pilot, and he isolated one of the legs on the helium system, and Hoot calls the ground and says, "Houston, Charlie's isolated the A leg on the helium system," and the ground says, "Roger." And I'm starting to think, you know, we agree, might be a nice call. How about good job? So we're driving along now with half of our helium system secured, and that pulls down the helium reg pressure quite a bit. Now we're getting concerned about operating with half of the system closed, when suddenly we notice the helium sensor starts to change sign. It's now positive, which says we're making helium, which is probably not very likely. So odds are it's a sensor. And so Hoot has Charlie open up the system again, and we call the ground and say, "Hey, it looks to us like it's a sensor, and we've opened up the system again," and the ground says, "Roger." So, okay, so much for years and years of training. The shuttle computers were always one of my favorite topics to learn about. This is a diagram out of the book. In the early days of the shuttle, I don't think it's true anymore, but in the early days of the shuttle, the software was actually on tape drives. And the computers wouldn't hold all the software you need, so you would reload the software as you change mission phases from this tape drive. And this is sort of the sequence of software loads that you'd go through on a typical mission. I won't bore you with that, although I kind of thought that was interesting stuff. The shuttle computer is this thing called an IBM AP101. It has 104,032 words of core memory, programmed in something called HAL. Now, George probably knows for sure, but I always thought HAL was an acronym. And then somebody told me, no, HAL is IBM with every letter displaced by 1. But then somebody told me it's actually a guy's name, this guy Hal Lanning at Draper Labs that was responsible for the programming language. That's probably the story I'll choose to believe. The computing power is 0.005% as much as an Xbox 360. Now, I don't have kids, so I don't actually know what an Xbox 360 is, but I think that's an impressive statistic. We upgraded it once in 1991, where we doubled the core. Now, people all the time say, you know, geez, computers are cheap. You guys it ought to be easy for you to upgrade your computers, right? Anybody know why we don't do that? Software. What's not cheap? Software, right. Software is expensive, and we have a lot of verification history on the software, and it works. And my understanding is that, you know, in their tradition, if you find something works, stick with it. The Russians in the Soyuz still use a 1974 computer. Billy probably knows if that's right. We did finally come into the 20th century, I guess, with glass cockpit. I never got to fly a vehicle with glass cockpit. I did have one experience, though. This is the main engine chamber pressure gauge, and in Discovery, the first time we flew it, they had changed the tape meter into an LCD meter. That was the only electronic, sort of modern, up-to-date display we had in the vehicle. And I don't remember if that was a test, or maybe they just couldn't buy any of the old tape meters anymore. But, in training, it was all fine. And then the day we launched, as soon as we lifted off and rotated and the sun was coming in the window, you couldn't see the PC gauges anymore. You couldn't read it. That was kind of stressful, frankly, because you have all these procedures you train for that in part are based on, what is the PC meter telling you? And what it was telling me is I don't like it. I want the old one back. We did eventually get a glass cockpit in the shuttle, and I probably shouldn't tell this story, but I did work on that back in the 80s. When I say work on it, what I was really working on was advocating for advanced controls and displays to the Orbiter Project Office. And they were very reluctant to add capability to the shuttle. One of the things about glass cockpit, which is nice, is you can actually program, the displays are computers too, and you can program them and add computing power and situational awareness, frankly, to the crew. I think if they had been able to keep buying the old ADIs and HSIs, we probably never would have got the glass cockpit, but eventually they couldn't buy them anymore, and they had to go to the glass cockpit. And I remember Dan Germany, who was the Orbiter Project Officer at the time, telling me, well, okay, you guys can have glass cockpit, but you better not do anything with it that is more than you do today with the current displays and controls. He didn't want us using that new capability. I want to talk a little bit about the shuttle design philosophy, because I think it's really interesting. We were always referred to it as fail-op, fail-safe. What that means is fail-operational, fail-safe. More specifically, you can suffer a failure and get the mission done. And you can suffer a second failure in any system and be able to come back. And the thing that was really fascinating about that was it really forced us to deal with how the different systems played together. I mean, this is a very simple and reasonable sounding approach, which I thought was fascinating and tremendously challenging to implement. And I don't know that I really have the time to tell the story, but since it was 30 years ago, 2 days ago, we learned how the primary software and the backup software played together. The reason we launched on April the 12th, as George knows, is because we scrubbed on April the 10th, STS-1. And the reason we scrubbed on STS-1 on April the 10th is because coming out of T-minus 20-minute hold, John took the backup computer to run, and it wouldn't track the primary software. And that was certainly a no-go condition, and people, I think, at least people around me, thought that this was a problem with the backup computer. And Randy Stone was a DPS officer on console that day, and he was all over it, and he knew it was a problem with the primary flight software. And Randy told me, because he and I talked about this, because I'll tell you in a second how I was involved, but the CAPE was continuing to do troubleshooting procedures on the computer. And Randy told Neil Hutchison, who was the flight director, said, well, they can troubleshoot all they want, but we're not going to go fly today. He was convinced it was a problem with the primary, and it was. And what happens, turns out, is that there is a very small probability, but a non-zero probability, that when you activate the primary software, which had been done days before, it'll go to the master timing unit and grab a time base, and it'll be incorrect. So when the backup computer is activated, it does the same thing. It grabs the time, and if its time is different, it assumes it's screwed up. But in this case, its time was right, and the primary software time was wrong. And it took a while for a lot of people to figure that out, although Randy somehow knew that right away. My job, because George had assigned me to the Shuttle Avionics Integration Lab for STS-1, was to see if I could reproduce this in the simulator we had in the lab. And that meant loading the primary software through a process called IPL, initial program load. And it's a fairly straightforward thing to do. And I think it's probably still true. I don't know if anybody keeps official statistics, but it's probably still true that I hold the world's record for most times IPLing a computer. and I don't remember the number, but it was between 175 and 200 times before we actually duplicated the situation in the lab. And we were able to clear the shuttle for launch 2 days later. So that's one example of how we learned how these systems play together. And I just thought that kind of stuff was really interesting. Here's another. If you had to abort, the commander has this thing called an abort rotary switch. And the one up here is a photograph taken on the real Space Shuttle Challenger by the real Space Shuttle Challenger commander, Gordon Fullerton, when they did the only real space shuttle abort during ascent in the history of the program. Hopefully it will be the only one in the history of the program. Fortunately, the engine shut down right when they crossed the abort to orbit boundary, so that was the abort they were able to do. And because the mission they had wasn't particularly sensitive to the specific altitude they were flying, they were able to do the mission completely, and it was all completely a success. And the way the shuttle abort rotary switch was labeled, you may be able to read it. It says off, RTLS, TAL, and ATO. And what happens, depending on where you have a failure, the commander then rotates the switch to the abort mode you want to execute, and then pushes the button. I think it's that one there. And then the computer understands you want to abort, and it executes the appropriate procedures. Well, turns out that after this happened, we were doing some tests someplace. I don't remember. A lot of these rotary switches exist in a lot of different places in the shuttle and in the simulators. We discovered a new failure mode. The new failure mode is you rotate the switch, and the knob rotates, and the shaft breaks. So you think you have just changed the position of the switch, and you push the button, and the computer reads wherever the shaft was when the failure took place. Now, if you want to do an ATO, and you rotate the switch to ATO and push the button and the shaft broke in the RTLS position, guess what? Shuttle's going to turn around and try to fly an RTLS, which would really not be what you want to do at that point in the ascent. And so this was something that we are now in violation of our fail-out, fail-safe philosophy. And the fix was actually relatively simple in this case. Again, this is just something that I thought was truly interesting. We changed the way we labeled the switch. So if you want, and told the software, of course, what the different switch positions meant. So if you wanted, you start with the second position being off. Then if you want to do the RTLS, you rotate it to the left. If it breaks in the off position, you still have a software command you can send that will have it do an RTLS. If you go to ATO in the right, and it breaks in the off position, you can still do an ATO through the software. If you go to TAL and it breaks in the ATO position, you can down mode from ATO to TAL. So we've again restored our fail-out, fail-safe requirement. And I just thought this was a really interesting way which we kept learning throughout the whole course of the program how these different systems interacted. Entry, of course, won't spend a lot of time on this, but you have to hit a very narrow corridor in order to manage both your energy and the thermal and G stresses on the vehicle. And the shuttle's been able to do that very well throughout its history. As I say, we never really met some of these cost goals, and part of it was because we had launch delays, and a lot of that was my fault. I don't know that people keep official records, but unofficially, I don't think there's anybody that has gotten into a shuttle vehicle more often with intent to fly than I, and so much that I don't even know what it is. It's 16 or 17 times.
I think you still have the record.
I think it's not challengeable any longer. George told you this story. He didn't tell you the whole story. We went out to launch on Discovery 24 hours before the pad abort. And on that day, again, we got down to 20 minutes, and Henry took the BFS computer to run, and it didn't go to run. And so we kind of knew we were done for the day. We sat there at T-9 minutes and let people talk about it, but they scrubbed the launch, and And as was typical of the team in Florida then and today, they were able to somehow heroically get out there and change out the backup computer, and 24 hours later we were ready to try again. And this time, when Henry took the switch to run at T-minus 20 minutes, he went to run. And that's all great. So we count down to 9 minutes where we sit there for the planned built-in hold. Now, the last time you can gracefully hold the launch is 31 seconds before T0. And so as we're counting down, going through our milestones, we get to T-minus 31 seconds. When the commander says, quote, "Well, gang, we're going to go now unless something really bad happens." And of course, we got to 6 seconds and the engine's lit, and we got to 3 seconds and the engine shut down. And I wish I had not told Hoot that story, because throughout our whole training for our second flight, every time we would get to 31 seconds, he'd say, "Well, we're going to go now unless something really bad happens." Early in the program, a lot of the shuttle's, this is the way I would describe it, a lot of the shuttle's margin was devoted to protecting for getting home. And that was appropriate early in the program. More and more, as we developed confidence in the shuttle, we devoted more and more of the capability to the payload and the mission. I mean, you would never fly at the altitude we fly to service Hubble if you were really worried about taking an orbital debris hit on your OMS tank, because you're not going to get home. But as we learned more and more how the shuttle worked, and we learned more and more what the real risks were, we were able to make these trades and devote more of the capability of the system to getting the job done. I was lucky enough to get to use the robot arm, which is a remarkable piece of equipment. 6 degree of freedom device we use for capturing satellites, releasing satellites, using it as a work platform for spacewalking astronauts. Someday I'll come back and talk about the human factors challenges that it represents. This is the control panel. One of the human factors issues I always had with it is that there's 2 controllers. So you got your hand on one and your hand on the other, and then you got all these switches that you're supposed to move. This is Hubble in the payload bay of the Discovery back in 1990, right before we lifted it up and deployed it for its now 21-year mission. Again, fail op, fail safe. What's the failure you want to protect against? Well, obviously you can see the Hubble is big and pretty much fills the bay. It's also fairly massive. On Earth it weighed about 24,000 pounds. The clearances are inches or less. So the failure you worry about is somehow the arm is going to move without the operator making a command. And since that could in principle happen, what's the backup? The backup is the operator, being skilled and cunning and well-trained, will notice that and apply the brakes and stop the arm. Well, how much time you have to react is a function of how fast it's moving and how far apart are the things you want to not come into contact. Things are very close together, and the telescope's very massive. And so in order to provide the operator with sufficient time to react, the software was configured so that it would limit the amount of rate you could command on the motors. That way, if the motor failed, it got a bad command, it still would only drive it at a very slow rate, and it would still give you time to react. Well, that seemed like a good idea at the time. And it turned out that as I was lifting the Hubble out of the payload bay, it seemed to wobble all over the place. And it didn't do that in the sim. And it was really challenging to try to figure out where the heck it was going. And make a long story short, when we got home and we went through all of this and did the debrief, what we found out was we had limited the rate to the motors to such an extent that the actual command was about the same size as the noise. And so it did sort of wobble all over the place. And we were able to take that experience and design a mode for the arm where you can tell it, hey, I just want to go straight up. and then you can put the command in, and it'll watch the other coordinates for you and make sure that it moves straight up. And that became a real asset to doing jobs like this in the future. That's actually on STS-82, where we were doing Hubble servicing, which brings me quickly to EVAs. The spacesuits were an interesting design. They were modular in construction, designed specifically for working on orbit. You wouldn't be able to walk on the surface of the moon in a shuttle suit. Because of this fail-op, fail-safe philosophy, we had to think about what are you going to do if you're working on Hubble. Normally, early in the program, if you're doing a spacewalk and you think about what's going to happen if my hook comes undone or my tether breaks, what's the next backup thing? And the answer is the shuttle goes and gets you. If you start to float away, assuming you're on good terms with your commander, he or she will come and fly the vehicle over and rescue you. Now, if you're attached to Hubble, that's not really a practical thing to do because Hubble would be damaged. Worse yet, if you're docked to the space station, you can't maneuver. And so what do you do if now you're a spacewalking astronaut and your tether breaks or your hook comes undone? Well, the first thought was we would develop this thing that we called a double tether protocol, which actually works to some extent if you're working on something like Hubble, and that says you have two tethers you have to manage, so if one comes undone or breaks, you're still hooked up. But Bill can probably tell you what it would be like to try to walk around the outside of the space station doing double tether protocols the whole way. And so to obviate the need for that, this thing called SAFER was developed, called for Simplified Aid for EVA Rescue, if I remember. And it's a little gas backpack that the EVA astronaut wears, and if his tether breaks, he flies himself back to the station or the shuttle. And any of you that want to be engineers and work in the space program, I would highly recommend spending some time thinking about doing better gloves. In the interest of time, I won't tell you my almost EVA story. We did launch a bunch of satellites early in the program, as George mentioned. We launched 3 on Discovery on the first mission. I don't know if anybody's launched 3 again. We did fly missions for the DoD. There was a partnership with the DoD early in the program. I think probably it may have been more of a shotgun marriage than a real partnership, but we did cooperate on a number of important missions. And the shuttle was able to recover or service on orbit satellites that had been in the wrong orbit or had not functioned in some manner, which was one of the things that we had promised early on that we'd be able to do. That's a picture of the moment of the deploy of the Hubble Space Telescope, and I don't probably have time to tell that story, but if somebody asks me later, I will. And of course, Shuttle Mir, we were actually able to figure out how to dock the shuttle with the Mir space station and transfer crew back and forth, beginning of our partnership with our Russian friends, and now the International Space Station. And how many people actually know that we've had humans constantly in orbit, Americans constantly in orbit for more than 10 years? It's a remarkable achievement made possible by the shuttle. I think I'll skip over this, although it's interesting to think about how do you train somebody to land a vehicle that flies as badly as the shuttle? And how do you get the shuttle back to Florida once it lands in California? I cannot give this talk without at least making mention of the friends we lost. This is famous, well, he's famous, he's in the Kansas City Star, I don't know if he's in the Houston Chronicle. Brian Bassett, who's well-known cartoonist and has a very fond relationship with NASA. He did this on the Challenger anniversary. We lost Challenger in January 1986. 4 of my classmates, Dick, Ron, Elle, and Judy. Judy and I flew together on Discovery in 1984. And everybody knows well that the cause of the accident was the solid rocket field joints didn't stand up to the cold weather. And then we had Columbia in February with the loss of crew and that was due to a foam strike on the RCC of the wing leading edge. Both of these things were very costly in a variety of ways, but both accidents did result in improvements in the program, including at least some chance of escape. We had a bailout system that could be used. Fortunately, it hasn't had to be used. And we had to give Warren the blue flight suits for the more cumbersome and uncomfortable orange pressure suits. Maybe part of the shuttle legacy is you know, put the vehicle on the top, not on the side. Talk a little bit about a couple of things, some of the science legacies. We use the shuttle as a platform for doing lots of things in orbit, including imaging the Earth. This is a picture taken from the shuttle radar topographic mapping mission. And that's the East African Rift Valley. That was a radar mission that mapped a high percentage of the Earth's surface. This is, I just went to the website and got it. This is the crew observations photograph of the week. It's remarkable how Crew Earth OBS has improved over the years. The cameras are better than we used to have. They carry lenses bigger than we were carried back in the early days. This is Ethiopia, and you can see water, irrigation, you can see a river, and you can see the sun glint. And that's one of the common ways that we can see water on their surface. This is just a picture that's always stuck in my mind. This was taken by Frank Culbertson aboard the International Space Station on 9/11. We had Space Lab and Space Hab, did a number of experiments in life sciences and material sciences. Of course, we launched the 3 great observatories, as George mentioned. We also launched major planetary spacecraft, Magellan to Venus, Galileo to Jupiter, and Ulysses, which was the International Solar Polar Mission. I showed this to my class. This is an image that was taken with the STIS, which was an instrument we installed on Hubble in 1997. This is an active galaxy, M84, and even in the early 90s, we weren't 100% sure that these weird things, black holes, really existed. And so this is an image of Doppler-shifted gas, red meaning it's moving away, blue meaning it's moving towards you, and by simple application of Newton's modification of Kepler's third law, you can calculate how much mass this gas must be orbiting. And by knowing how far away the galaxy is, you can know how physically large that region is, and it turns out there's, you know, a few billion solar masses in the size of something about the size of the solar system. And so Hubble, after 1997, proved that black holes really exist, thanks in part at least to the shuttle. We learned a lot about life sciences, how the body adapts. I am definitely not the expert on this, but exercise helps. I'm not sure if we know yet how much exercise we definitely need to counteract the effects of bone loss and deconditioning that happens from spaceflight. We've got a couple of data points. We kind of know what it's like on the Earth, and we kind of know what it's like in the microgravity that is shuttle and station. And the interesting question for future explorers is, what's the right trajectory? As we go from microgravity to 1G, does this curve represent the response of the system? Does this curve? We don't really know. That's a subject for hopefully future research. Turns out that astronauts are more susceptible to glaucoma based on tests the flight surgeons have done, based on exposure to radiation. There does seem to be a correlation between high altitude or high inclination and radiation exposure and the onset of glaucoma. So hopefully they'll be able to use what they find in some of us to understand that a little bit better. People used to ask me, did you always want to be an astronaut? And my answer was, well, not always, because astronauts used to be pilots exclusively, and I didn't want to be a pilot, I wanted to be an astronomer. But that changed initially in the 60s, but for good in 1977, when the program began to look for in addition to the traditional military pilots, scientists, engineers, medical doctors who'd be part of this new thing called the space shuttle. And those were the requirements. You had to have a technical degree, had to be able to pass the flight physical. You had to be between 5 foot even and 6'4". And I remember being in grad school at the time and seeing that on the bulletin board. There was this letter that said NASA on the top, and they were looking for astronauts. And I thought, wow, you know, they're talking about me. So I immediately applied and somehow managed to get through the system. Fortunately, I've retired now because I spent 30 years anticipating George coming up to me one day and saying, hey, you know, we realized we meant a different Steve Hawley. And we finally located him, and you're out of here. I don't want to leave this up here too long because I don't want to give you a chance to identify the one that's me. But this was the first group of astronauts that had women and minority representation. And people have suggested to me over the years, well, wasn't that a real culture change for NASA to have women and minority astronauts now? And I would say, well, yes, that's true. But I've confirmed my point of view with several of my colleagues because I say that the biggest culture change that the astronaut program went through was the introduction to the military officers, this group of hardcore civilians who approach problem solving in different ways. And I think that in the end, it made us all better for bringing those different approaches, different personalities, different kinds of backgrounds together for the betterment of the program. Leading to, among other things, the first time a shuttle mission was ever commanded by a female. This is Eileen Collins in the middle. She commanded the Chandra deployment mission STS-93 in 1999, and I was very privileged to be part of her crew. And the shuttle made possible spaceflight for a wide variety of individuals, including people like me, the non-traditional, non-test pilot scientists and engineers. We also had this class of non-professional astronauts called payload specialists and spaceflight participants such as Krista. And we also flew representatives of other nations on the shuttle, and 1 congressman and 2 senators. The congressman is now a senator. And since he is still a senator, I will not tell you any stories about flying with a congressman. And as I recall, we almost flew the Secretary of the Air Force back on 61A, which would have been the Vandenberg launch that was canceled after Challenger. Some spin-offs. The shuttle has become part of our culture. In many ways, Space Cowboys is important to me because it turns out they were filming at JSC right when we came back from STS-93, and they came to our crew party, post-landing party, and I had a chance to talk to some of the cast members, and I remember Donald Sutherland being truly interested in the space program. I think Tommy Lee Jones couldn't have cared less, but Donald Sutherland was really interested in how it really was to fly the space shuttle. Part of the public legacy were the IMAX movies that we made, taking the IMAX camera that you see here on board. This was on board Discovery in 1984, and making Dream is Alive, Destiny in Space. There's a new one on Hubble that came out last year, I think. That's the camera. It's a huge camera, and it was kind of frankly, it was a pain to operate, but the product was really outstanding. And I will take a minute just to tell you this story. That's Judy, Judy Resnick, and maybe 2 stories. You see her hair. Well, that happens in 0G. And I think it was about flight day 3 or flight day 4 of the mission. Of course, there's a tradition that the crew is awakened with a song played by Mission Control, the wake-up music, and they played the song from Hair. And I think that was the first time Judy realized that people on the ground had seen her hair. And I won't tell you exactly what she said. In fact, I probably shouldn't even try to characterize what she said. But that's just background. The real story is that's the IMAX camera, and it has a belt drive, and it drives a 70mm movie film through this camera at high speed. In fact, if you turn it on and you're not anchored to anything in weightlessness, you will begin to torque. Well, in one of the dumb calls of all time, we, the crew, decided that we would save weight and complexity by leaving the belt guard at home. And I was down on the middeck one day when they were upstairs filming. I heard the camera come on, and then I heard this blood-curdling scream. And I went as quick as I could upstairs, and Judy's hair had gotten caught in the belt. And there was film and hair all over the space shuttle. And the ground called us up and they said, hey, we noticed that the IMAX circuit breaker blew. And we said, yeah, we noticed that too. And we never told them what really happened. But we spent a day going around trying to clean up pieces of film and pieces of Judy's hair. So, you know, making some of these, you know, public outreach movies is not without its own peril. That is a summary of the shuttle fleet. Discovery is a fleet leader, had its final flight in February. Endeavour is next. I think it's now April 29th. I haven't updated the slide. And hopefully Atlantis sometime this summer, because it'll be really important to get some of those parts up to the space station before the program is retired. Anyway, I want to thank you for letting me reminisce a bit with you, and I'd be more than happy to stand here and answer questions for as long as you have the patience to ask them.
Very well done, Steve. Any questions? Yes.
Whatever happened to Vandenberg? Because I understand they built this multi-billion-dollar thing, and then it just like disappeared from everything, just vanished. So.
Well, George probably knows better than I do. There were technical problems. In fact, if I remember right, we were building different solid rocket motors. There were the flex, the fiber, what was basically a composite material. It would be a little bit lighter weight. I think probably the real answer is that after Challenger, it became clear that the Department of Defense really wanted to have its own and redundant launch system. We didn't want, you know, everything that this country can launch dependent on one vehicle. And I think they moved away from shuttle and towards the development of their own fleet of expendables again.
That's right. Yeah.
If you have to be going 17,000 miles an hour to orbit the Earth, then what would be the point of going Mach 25 to reach something that's orbiting if you needed to get to it? Because wouldn't you go past it?
Well, yeah, that's a really good question. Mach really refers to, you know, speed through the air.
Right.
And that's not a sensible concept if you're in the relative vacuum of space.
Okay.
So, but, you know, if you 17,000 miles an hour is about 25,000 feet per second, and 1,000 feet per second is Mach 1, so it's about Mach 25 is how we refer to it.
Okay.
Yes.
The lost satellite, the Earth observing satellite that's supposed to go to the Lagrangian point and help do the observations of the total Earth emissions for the energy imbalance issue. Any chance of that getting out of the warehouse and getting?
I'm not familiar with that satellite, so I guess I can't give you an update on its status.
Well, actually, I do know a little bit about it. They're talking about using it to refurbish. I think it's Discovery.
Discovery.
Yeah. And they're talking about using it to be a solar wind monitor out at L1 and refurbishing it and being the ACE replacement. So, of course, you could do that science with a much lighter weight spacecraft. So it's still to be determined whether it's going to be the new solar wind monitor or whether they're going to do a smaller, lighter mission. But that's the present plan as how they might reuse it.
NASA's trying to get it to NOAA so that NOAA can then launch it to do this job. So it's an interagency issue at the moment.
Okay.
what's your best guess that what's next if we abandon, if we walk away from the shuttle system? What are we going to replace it with? What's the quid pro quo? I mean, something big. I mean, not something small like algebra.
Well, I wish I knew the answer to that. According to current policy, what's to replace it is whatever the commercial sector can come up with. And that'll be to low Earth orbit, of course. It won't be something that'll take us to Mars. So it remains to be seen. I've got several concerns, frankly. One is, and people may have thought about this, and there may be an answer, and if there is, I'd love to hear it. But I'm less concerned about whether a commercial provider can really develop a reliable launch system. I'm more concerned that I don't know where the market is. And if there's no market, they'll go away. And if they go away, we won't have anything. So I'd like to see some effort, and maybe it's happening and I just don't know, but some effort devoted to developing a market for a capability. You know, we don't need 3 or 4 launch providers as much as we may need a launch provider and then several companies thinking about what to do once they can get either people or things or both into orbit. I'm also a little concerned, frankly, that the longer we go without our own ability to launch our people, that may become the new norm. In which case it might be really hard, 6 or 8 or 10 years from now to develop the national will to go back and reinvest in that capability that we have lost. I don't know. You guys probably have your own ideas about how reasonable a threat that is.
Can I follow up on that question a little bit? I'm not sure this is easy to answer, but the commercial route to space, some companies thinking of proposing to use the shuttles as that vehicle, which I think is, we had a nice meeting here a few weeks ago where that sounds like a great opportunity because of the shuttle's capability. How does the decision to museum these guys affect the ability to then reuse them for launch? Do you have any?
I have no idea.
Yeah.
I have no idea.
It just came out today about whether.
Yeah, I heard that. I don't know. I mean, my reaction to it would be that I don't know why you would make that announcement if you were going to be open-minded about other possibilities, but I don't have any insight into that.
Okay, United States use a customary system of units, pounds, feet, and so on. And Europe and Russia, they use a metric system, meter, kilograms, and so on. During your international flights, do you feel some inconvenience or problems with these different systems?
Actually, Bill's probably the best guy to answer that. Did we have any issues that you're aware of?
No, it's I mean, the short answer is no. It's more interesting than it is inconvenient, and if it's really important to be precise, you go to go to your computer and get a nice precise conversion. But especially if you're operating on the International Space Station, just like any good garage, you have a combination of metric and English unit tools, and you go get the right tool for the right job. And if you're operating a system, the system will present itself in units. Now, the U.S. segment is very much going more toward metric as far as measurements and things like that. But still, you become pretty adept at jumping from one set of units to the other. The real challenge is to make sure you're very, very meticulous in the design phase and in the interface, and how you configuration manage the interface between a system that's designed under a metric culture versus a system designed under using the U.S. or English units.
Thank you.
Were we? Let me ask Bill a question. Were we not going to try to go metric for Constellation? Do you remember?
I don't know.
That was discussed but never programmed by Farm.
Thanks.
Any other questions?
As a continuation of the question about now that the space shuttle program is going to be discontinued, what becomes of the space station?
Well, I would say truthfully, that's a good question. The plan is to operate it through the end of the decade. It is now complete and able to accommodate up to 6 people at a time. The thing that makes me equivocate just a little bit is a lot of the support that the station plans on is provided by the shuttle. Part of the reason why this mission later this summer is so important is we have a number of things that only can fit on the shuttle that we would really like to get up to the space station in case they need them over the next 9 or 8 years. So the answer to the question may be it depends on how things play out. But it's possible, perhaps even likely, that over the next 8 or 9 years, there will be things that happen that we could have dealt with if we still had the shuttle, but we can't deal with because we can't get the replacement part on orbit or whatever, or get something back. I mean, George and I were talking before about the fact that the design of the station involved replacing these user racks and bringing them down and bringing new ones up, and of course you won't be able to do that. I mean, maybe a commercial provider will build something that can do that. I don't know. But the whole design of the station was based on the availability of the shuttle to bring stuff up and bring stuff back.
And there are still people there working and stationed there?
Yeah, there's still, and the plan is to have people continue to work on station for at least until the 2020.
How do they get home?
Well, right now they get home on the Russian spacecraft. That's how they get up.
If you look at the shuttle missions this past year that went up to the station, each of those missions took up a substantial amount of cargo, but they also brought back a substantial amount of cargo. The last time when we didn't have a shuttle was after the Columbia accident, and we had 3 crewmen on the station, and because we didn't have a shuttle and couldn't support them logistically, we had to go down to 2 crewmen. We're now up to 6, and without a shuttle, the shuttle contributes a lot of water to the station because of the fuel cells, and in addition to that, just general logistics. And they were designed to be operated together. The shuttle was going to be supporting the space station. So I think when we talk about going to 2020 without a shuttle, we're taking a substantial risk. Yes?
How many pounds of cargo can y'all bring back down with the shuttle?
With the shuttle, we can bring down 60,000 pounds. And right now, without a shuttle, the Progress can't bring any cargo down, the ATV can't bring any cargo down, the Soyuz can't bring any cargo down, the HTV can't bring any cargo down. Some of these commercial users are talking about having some capability to have some limited amount of cargo back down, but that is, as Steve said, is still improving. Yes?
Are you saying then if we did a mission to Mars, we would probably need some other type of vehicle to go up and down to the space station to use it as a waypoint?
Well, if you're going to go to Mars, you really ought to build on the investment you have right now with the shuttle and the station. So if you're going to develop an architecture to go to Mars and go back to the moon, we should have really built on the shuttle and the station. Constellation threw both of those out the window and came up with a whole new concept that gave us a spacecraft that we flew 40 years ago and landed in the water. We ought to look at developing a scenario to go to the moon and Mars that would utilize that foundation and that investment we've already made in the shuttle and the station.
Amen.
Just wondering, we have the heavy lift capability, I guess, with Delta. I think there are a couple of different versions. And I wonder if those could carry the heavy cargo like the fuel and the water or big things up there, because, you know, it seems like that is stuff that's...
You'd have to have some way to get them over to the station.
Okay.
And it isn't just a question of weight, it's also a question of volume.
And a space tug to get it from low Earth orbit to station, back and forth, like the ATV and the HTV things do now.
Yes.
Is there a commercial equivalent to the mission control? Or does NASA do all the mission control for the commercial?
The mission control so far with the commercial people they've been controlling it themselves. So right now, if you look at mission control in Houston, when that last shuttle goes in June, the only control we'll be doing out of Houston is going to be the space station, which we share with Russia. Which means there's going to be a substantial layoff of the workforce here in Houston. Yes.
You're mentioning not being able to bring stuff back from the station led to the thoughts about increasing amounts of space junk in the next 10 years. Do we have any plans to decrease the hazard from that?
Well, people have looked at some techniques. I don't know of any that are particularly promising, and the mitigation plans all, as far as I know, affect the front end. You know, how do you keep your stuff from contributing to the growth of the environment, rather than how do I get stuff out of the environment that's already there. When I was still at JSC, our group did a study on the debris environment. This would have been probably 2004, 2005. And at that time, the outcome of the study was that if nobody ever launched anything ever again, the debris environment would go up for 50 years and then it would go up exponentially. And that's because collisions make more debris at a more rapid rate than natural decay will cleanse the environment. And that was before the Chinese weather satellite and other things that have even made the debris environment worse. So I'm not aware of a mitigation that can right now cleanse the environment, and the focus has tried to be on how to keep it from getting worse.
I think we have time for one more question, and then we have a reception plan. Yeah.
Have they made a serious attempt to simply mothball the shuttles right now until a new administration comes in to make some common sense decisions?
I don't think they have a good plan to mothball them. They ought to have a good plan to keep them flying. That's what they ought to have.
Yeah, but I mean, and we know that's not going to happen until we took this administration in there.
Well, you have to bear in mind that the shuttle cancellation was done in a previous administration, and the new administration's taking that on board and then making a more ridiculous situation of keeping the space station going without a shuttle program. So, you know, a new administration, I don't know what they're going to do regardless of what their strength is.
United Space Alliance has submitted a proposal to NASA to operate the shuttles commercially. I don't think you've got any reply to that, have you?
We visited NASA just last week. We have another series of meetings, but it's getting down to the end. If you read the announcement today, it said they would ship the shuttles to the 4 locations by the end of 2012. So there's not much time. And in the meantime, to answer your question, we are not doing anything to the shuttles as they return that would keep them from flying. But by the time Atlantis flies, if the decision is not to fly, then we will put them in a preservation and museum status, and they would not fly.
Yeah, which would be difficult to recover from, yes, I understand.
Is it, let me ask Howard this question, what is it, you know, part of the problem, of course, would be sustainability, and is it still possible that there are suppliers that if we chose to, for some reason to continue to fly 1 or 2 flights a year, that we could sustain that?
Yes, NASA's done a good job, and all of us, all of the primes have done a good job to keep the suppliers interested and available. I've talked here a couple of weeks ago or a month ago. The long pole is building external tanks, and that puts the next shuttle flight after Atlantis at least 1.5 years away before you'd have another tank. But Bill just gave us the authority to preserve the 17-inch disconnects, for example. And those are being moved to Michoud, to MAF, so that they would be available. That was another long pole.
An expensive pole, yeah.
Well, thank you all very much for coming, and